Lecture 19b, example number 3, Killing equations, spherical coordinates. Let's continue. You see, from the lecture 19a, we derived equation 1, 2, and 3. I just copy from there and wrote over here. So, this is step 3. You see? Following step 1 and 2 from lecture 19a. So, lower indices using the metric. You see, there's a property of the metric. You see, this u here is a covariant, u theta is contravariant. Then this is the metric, then we relate, okay, the contravariant to variant component. So, likewise, u phi, a g phi phi u phi. This is sine square of u phi. Because the metric, this applied to the spherical coordinates, this g phi phi is sine square of theta. And this here is 1. You see, this is 1 here. So this is 1. Now, and this is sine square of theta. Now, writing everything in terms of the contravariant components, u theta and u phi, yields. So, there's the first equation over here is equal 0. This u theta is a phi. This is a constant in theta. Okay, that's important. It's a variable, okay, but it's constant in theta. This is a of phi. Does not depend on theta. You see, that's what means this partial differential equation over here. So, the equation that u phi is sine square, in this case u phi. This again, this is the metric, okay, you see here, this is covariant, this is contravariant components. Now, you plug, you see, this u phi on this equation over here, okay, this equation, partial u phi. So, you have partial of respect to phi, sine square of theta u phi plus sine cosine of u theta. You see, it's quite easy, as we derived in the previously. You see, so this I take the derivative, the partial derivative, okay, with respect to phi. Attention, you see, theta here, okay, the sine square will be out of this operator here. So this is sine square of theta. That's the partial phi u phi, sine cosine of u theta. That's quite easy to derive this. So then you can obtain just this term over here is this one. You see, you just this is minus sine cosine sine square. If you cancel here, this will be cosine divided by sine. So this cotangent of theta, this is u theta. You see, that's important. The left-hand side is a function only of phi. The right-hand side is function of theta. But they must be equal. So there is only one way to relate. A function of phi is equal function of theta. This is equal to a constant lambda. Now, this constant must be 0 since you preserve the definition, okay, of the lead derivative of the metric must be 0. That's why lambda must be 0. So, partial phi u phi is equal to 0. Now, I obtained the components, the contravariant component u phi is equal constant. And also cotangent theta u theta is equal 0, since u theta, you see, u theta, this is equal to lambda. You see, if it's 0, lambda is 0, u theta must be 0. So this over here. So I have the components of the Killing vector. You see, u theta is equal 0 and u phi is equal c. Now I write the vector, okay? The vector u expressed, okay, in the covariant basis. See, this is covariant basis. This is contravariant components, okay? Both belong to the vector space, not the dual. You see, we discussed this previously in other videos. So then that's the solution. You see, the Killing vector u is 0 times this base here plus c times this base vector. So u is c partial of phi. You see, this here, just to understand, is just partial of phi. You see, which I represent this as this, denoting this here. Now, you see, this generates rotational symmetry around Cx. Don't forget, because in this case, phi is the azimuthal. You see, you have a sphere, okay? This varies from 0 to 2 pi. Theta is the polar coordinates. So for each theta constant, then I have a rotational symmetry, okay? Varies from 0 to 2 pi. So I'm saying this here. Since phi is periodic, you see, phi belongs to the interval, okay? That's a closed interval 0 that's open. You see? There's an interval between 0 and 2 pi. That's a full rotation. This brings you back to the same point, you see, because it's periodic, okay? So for each polar theta is equal constant. Again, theta is polar coordinates. So geometry coordinate convention. C takes c is equal 1, so u is just partial of partial phi, or partial derivative. Now, that's important message. So unless there is a specific physical or geometrical reason to choose otherwise, in this case, the natural choice is, in this case, c is equal 1. That's the final answer. So my Killing vector is partial derivative with respect to phi. You see, and phi again is the azimuthal coordinates, okay? It rotates. Now that's it. You see, I emphasized, okay, that example 3 is different from example 1 and 2. Why? Because in example 1 and 2, the goal is to verify if it is a Killing vector. This one is just the opposite. You see, I want to find out, to get the Killing vector. It's different. So I have to solve differential equation. See, that's it.